Section 8.6, solving exponential and logarithmic equations. Our learning targets today, there are 3 of them. Solve exponentials, solve logs, and determine if we have extraneous solutions, which we've done in the past. Really, solving combines a number of steps we've done in the past, linear solving steps, logging both sides, using some log properties, evaluating exponentials, all those are kind of being combined here. Let's start with example 1. Key thing with number 1 is we want to see if we can get the same base on each side. The base on the left side is 2. Right now the base on the right side is 32. But 32 is a power of 2. So off to the side here, we are thinking, a little thought cloud, that 32 equals 2 to the 5th. So I'm going to rewrite here. I'm going to get 2 to the 4x equals 2 to the 5th in place of 32, and then raising to the x minus 1 power. X minus 1 is a binomial, so after a rewrite here, we're going to get 2 to the 5x minus 5 power. Since we have the same base on each side of this equation, I can now say that I'm going to kind of change gears a little bit. That 4x has to equal 5x minus 5. I go ahead and subtract the 5x over to the left. And when I solve, I get x equals 5. Again, we need to get a common base if we have this situation. Example 2, just a standard unknown as the exponent. We're going to go ahead and we're going to take the log of both sides and then use a property to get at that x. So I'm going to do the common log to both sides. I'm going to hold the x via my property with logs. That's the power property of logarithms. I'm going to divide both sides by the log of 4. And that is going to give me approximately 1.95 for my value of x. Continuing here. Here's a combination of example 2 with some linear solving. Subtract 3 from both sides. I get 5 to this exponent equals 22. Now I'm going to go ahead and do the common log to both sides and do my power property of logs. So I'm going to get x plus 2, my power up front, log base 5, and log 22. I'm going to divide both sides by log of 5. And then I'm going to subtract the 2 over. So that will leave me, after I calculate the log of 22 divided by 5, subtract 2, I am going to end up with negative 0.079. My answer. Example 4, very similar to example 3. Linear solve step. Whoops. Divide by negative 5 step. And now our log step, but this time I'm going to do the the natural log, so power out front, natural log of e equals the natural log of 0.6. Just write that. The natural log of Euler's is 1, so that cancels. I get negative x equals this, divide by negative 1, and I get x is about equal to 0.511. As far as rounding, 1 decimal place or 2 is just fine. Now, solving these log equations, a little bit different strategy. We'll just go through these 3 examples. Similar to our first example, example 5, I have a same log on both sides, log base 4. If log base 4 of x plus 3 equals log base 4 of 8x plus 17, that means I can actually ignore the log parts and say x plus 3 has to in fact equal 8x minus 17. So subtract x from both sides, subtract 17 from both sides, divide both sides by 7, and I get x is negative 2. Continuing on here, in this case, I'm going to write this log statement as an exponential. My base is 4, my power is 2, and has to value to x plus 3. I have 16 here, x plus 3, subtract 3 over, and I get x equals 17. Example 7, linear step here of subtracting 1 over. That will give me negative 2 times the natural log of x equals negative 5. Divide both sides by negative 2. That will give me the natural log of x equals 2.5. Rewrite this as an exponential. Base here with the natural log is e to the 2.5 equals x. Now that could be an answer, or if we wanted to get a decimal approximation, we would end up with a 12.18. So steps, converting back and forth between logs and exponentials, doing some linear solve steps by adding and subtracting, multiplying, dividing. So all sorts of things going on here. And that will take us to the end here, the change of base, the last couple of problems. Actually, we need to add a problem here. Your example 8, I will write it down. Now, this is a type problem, so this is example 8. Plus lowercase 2 x minus 7 equals 3. Okay. Now with this, since we have a log base 2 expression plus a log base 2 expression, we're going to condense this into log base 2 of x times x minus 7 equals 3. Okay. So now I'm going to rewrite this as an exponential. So I'm going to say 2 to the third. So the base of 2, power of 3, and I'm going to go ahead and distribute this. I'm going to get x squared minus 7x. Well, 2 to the third is actually 8. I'm going to subtract that over. And to finish this, we will need to factor. And we can do our factoring. X, the 1 times the negative 8 is negative 8. Middle term, negative 7. What are the factors of negative 8 that add up to negative 7? And I see negative 8 and a plus 1. So what that now means is that I can say 0 equals my binomial x minus 8, x plus 1. So my possible zeros are negative 1 and 8. So So what I have to do now is check these. I've got to check these with my original equation here. Now when I plug in -1, when I plug -1 back into my original here, I'm going to plug it in here and plug it in here. I get -1, which I see right now is a problem because I cannot evaluate or get an answer when I take log base 2 of -1. So this does not work because it violates one of our original rules with logs. Now I'm going to take 8 and plug it in here and get 1. I'm going to take 8 and plug it in here. Okay, so log base 2 of 8 is 3. So I get 3. Log base 2 of 1 is 0. And these two add up to be 3. Yes, it does. So 8 will check. So that ends our lesson on 8.6.